Hi, Professor Collins here again to talk more about the concepts from Chapter 8, the mole concept. When it comes to that very important concept in chemistry, I like to think of solving problems using a flow diagram, with the mole being the center of our diagram. Flow diagrams are used by computer engineers and other types of scientists to help write algorithms and to solve problems. For example, we know that Avogadro's number 6.02 times 10 to the 23 is equal to the number of particles in 1 mole. So to convert from particles to moles, I simply have to use Avogadro's number. I'm going to abbreviate that by N capital A. Recall, particles can either be atoms or molecules. We're talking about Avogadro's number of atoms if we're talking about the substance gold, magnesium, sodium, and or we talk about Avogadro's number of molecules if we're talking about substances with multiple types of atoms like water or glucose. So the way this flow concept works is I know that given the number of particles, which can be atoms or molecules, I can determine the number of moles by dividing by Na, which is Avogadro's number. Using this flow diagram, if I'm given a problem where I know the number of moles, I can determine how many particles that is, how many atoms or how many molecules, by multiplying times Avogadro's number. Extending my flow concept further, I know that I can, if I know the number of moles of any substance, I can determine the mass of that substance using a unit factor called the molar mass. Remember, the units of mass are grams per mole. Every mole, for example, of water has a molar mass of 1 plus 1 plus 16, or 18 grams per mole. So again, the mole is the center of my flow diagram. I can multiply by the molar mass of any substance to get the mass of that substance, or I can divide by the molar mass. If I know the mass of any substance, I can divide by the mass, which is always a mass in grams, to get the number of moles. There's one more direction I can go in my flow diagram, and that's between moles and volume. Volume at STP. STP is a term used for standard temperature and pressure. That's when temperature equals 0 degrees Celsius and pressure equals 1 atmosphere. To travel this direction in our flow diagram involves using the unit factor of molar volume. Recall from the lecture, the molar volume of any gas at STP equals 22.4 liters per mole. So I can multiply by the molar volume if I know the number of moles to get the volume in liters. If I want to go from a volume to the number of moles, I divide by the molar volume of 22.4. Now, using this flow with moles at the center, we can solve a lot of stoichiometry problems, a topic we'll be talking about in Chapter 9, but also any kind of mole question related to atoms or molecules, mass in grams, or volume in liters. The mole is the center. These directional arrows show us how we can go from one direction to another. Now I'm going to go through a series of problems, a handful of problems, to illustrate how this flow diagram can work to help us solve chemical problems. Here's the first problem I'd like to solve. How many atoms are there in 0.12 moles of sodium? Well, we're going to look at our flow concept. We want to find out how many atoms, which is one type of particle, there are given a certain amount of moles of sodium. So I want to go this direction from moles to particles. In this case, it's going to be atoms. And I write that down this way. First, step one of my process is to write down what I'm looking for. number of atoms sodium. Part 2, what am I starting with? Step 2 rather, 0.120 moles of sodium. Step 3, to get from 0.12 to my answer, I'm going to, as I showed in the chart, I'm going to multiply by Avogadro's number of atoms, because I know there's 6.02 times 10 to the 23 atoms in every mole of sodium. My moles cancel as units. All I have left is atoms, and that's what I want in my answer. And the answer is 7.22 times 10 to the 23 atoms of sodium. Let's solve a similar problem, but we're going to go in the opposite direction. Let's calculate the number of moles if I'm given 1.25 times 10 to the 21 atoms of potassium. So this process would be write down first what you're looking to find, how many moles of potassium. Step 2, write down what you're starting with, 1.25 times 10 to the 21 atoms. Now this time, we're going to divide by Avogadro's number. Using that flow diagram as I showed you before at the initial part of this lecture, we want to this time divide by Avogadro's number, 6.02 times 10 to the 23 atoms of potassium and every mole of potassium. So my atoms cancel. The number that's left is moles. And if you want to try this out, and the answer turns out to be, the answer becomes 2.08 times 10 to the minus 3 moles potassium, which is 123.00208 moles of potassium. Before we move on to the next type of calculation, I will make a mathematical correction. This first problem turned out to be 7.22 times 10 to the 22 atoms of sodium. That's smaller than Avogadro's number, and it should be, shouldn't it? Because you have a fraction of a mole to begin with. So let's move on to the next type of mole problem in chemical analysis. Okay, let's turn our page over and solve another type of mole problem. In this problem, we're going to determine the mass in 2.01 times 10 to the 22 atoms of sulfur. Basically, if we want to find the mass, we're going to determine how many grams are there in 2.01 times 10 to the 22 atoms of sulfur. If you look at our flow diagram from the first part of this lecture, let's follow the directions we need to go. We're given the mass in grams. We want to find the mass in grams. We're starting with a number of atoms. We're going to start with atoms, which is one type of particles. First, divide by Avogadro's number to get the number of moles of sulfur. Then we're going to multiply by the molar mass of sulfur to get the mass of sulfur. So it's going to be 2 steps. In the first step, we're going to take what we're given, 2.01 times 10 to the 22 atoms of sulfur, divide by Avogadro's number to get us to the number of moles of sulfur. In the next step, according to my flow, I take the number of moles of sulfur that I've calculated after the first step and multiply by the molar mass of sulfur. Now, sulfur is in its elemental form. The molar mass is simply the same as the atomic mass of sulfur. So you can get that from a periodic table. Every mole of sulfur has 32.07 grams of sulfur. Now, you might look at a different periodic table that has fewer numbers of significant figures. You might see one that says 32.1. Either of those numbers are fine. You can do that to determine the mass of sulfur in grams. So see how your units are cancel appropriately, atoms and moles, so that all the units that are left are what you get in the answer. And the answer is 1.07 grams of sulfur. That's what you get if you have to start with 2.01 times 10 to the 22 atoms of sulfur. Here's a similar problem, but it's going in the other direction. Let's answer this question. How many molecules of O2 gas are there in 0.470 grams of O2 gas? This time, I'm going to look at my flow. I'm given a mass, shown here in the diagram. I want to find the number of molecules, which is one of the types of particles. We're talking about molecules here because O2 is a diatomic. It's one of those 7 elements that's always a diatomic. So it's another two-step process, but this time we're going from this direction to this direction. Beginning with mass, calculate number of moles by dividing by the molar mass. Then we calculate the number of molecules by multiplying by Avogadro's number. 2 steps. So let's follow our 3-step process. First, we write down what we're looking for, molecules of O2. The next step is to write down what we're starting with. That's the mass of O2, 0.470 grams. So, as I said, again, 2-step process to go from mass to molecules. We first divide by the molar mass of O2. Now, the molar mass of O2 is not just one oxygen atom. One oxygen atom has a mass of 16. O2, of course, is 2 atoms, so it's 16 plus 16, or 32 grams in the denominator, so that your units grams cancel. After the first step, you've calculated the number of moles of O2. Now we want to turn that into molecules of O2, and we do that by multiplying by Avogadro's number, which is always 6.02 times 10 to the 23. Molecules, not atoms, because we're talking about something that has more than one atom in it, O2. Does that mean molecules in every mole of O2? And the answer you should get after dividing the mass of 0.47 by 32 and then multiplying by Avogadro's number should equal 8.84 times 10 to the 21 molecules of O2. Let's do another type of mole problem, this time involving the volume and the molar value. As in all the problems, we're going to use the mole we will have to calculate moles at one point in our problem solving. Let's solve the problem. How many liters of gas, and this is how many liters at STP, of nitrogen gas, N2, are there in 2.0 grams of N2? Well, how do I start my problem? I first write down what I'm looking for. That's liters. I next write down what I was given, 2.0 grams. In my flow diagram, you'll see I'm going to start with a mass, divide by the molar mass of that particular gas, which is N2. That will tell me how many moles of N2 I have. Then I will multiply the number of moles of N2 by 22.4 liters per mole to get the number of liters at STP. Let's do that in the problem below. The first step, we look at the periodic table and determine that the molar mass of N2 is basically 2 nitrogen atoms, right? Each nitrogen atom, if you look at the periodic table, has a mass of 14.0. So 2 nitrogen atoms will be 28.0, which means I have 28.0 grams of nitrogen in every mole of nitrogen. After the first step, you see that the units grams are removed, and you have moles. After we have number of moles, we multiply by the molar volume at STP, which tells us that every gas has 22.4 liters per mole. In this step, the moles will cancel out from numerator to denominator. So your final answer will be in liters of N2 at STP. So we divide by the molar volume, 2 divided by 28, and then multiply by we divide by the molar mass of nitrogen, which is 28.0 grams per N2. Divide by the molar mass, then we multiply by the molar volume, which is liters per mole, to get the answer, which turns out to be 1.66 liters of N2 at STP. Let's take a minute to summarize those first types of problems. Remember, in our diagram here, I illustrate how the mole is the center of our strategy, where we can go from one direction to the other in any way we need to. And we really just need to know 3 different factors. 2 numbers we have to memorize. The third number we always get if we have a periodic table present. 1 mole of any substance is always going to equal Avogadro's number of particles, which of course can be what? Atoms or molecules. 1 mole is also equal to the molar mass. And if we're talking about mass, you know we're going to talk about units. So the molar mass has units of grams per mole. If we have a periodic table, we can always determine what that is. And the other number we have to remember to memorize besides Avogadro's number is that called the molar volume. In every mole, you have exactly 22.4 liters if you're at STP, temperature of 0 Celsius, and pressure equal to 1 atmosphere. So again, memorize two numbers, have a periodic table present to come up with that third type of unit factor, and you can solve any types of, many types of mole calculations as we have in the last handful of examples. Let's solve one more type of mole problem, then we're going to move on to other types of calculations. How about this problem? What is the mass in grams of ozone if you have 3.36 liters of it at STP? Let's look at my flow diagram. We're starting with a volume in liters at STP. We want to convert that to moles, and then we convert that to mass. So the first step will involve dividing by the molar mass to give me the number of moles of ozone. And then I'm going to multiply by the molar mass. First step I divide by the molar volume to get moles. The second step involves multiplying by the molar mass of O3 to get the mass of O3. Okay, let's do that. The first step involves taking the volume of O3 that you're given at STP and converting that to moles of O3 by dividing by the molar volume. The molar volume is always 22.4 liters per mole if you're at 0 degrees temperature and 1 atmosphere pressure. The next step involves taking the number of moles that you've generated, because liters have canceled from the numerator and denominator in the first step, and so you're left with moles as your units after the first step. Then you're going to multiply this times the molar mass of ozone. That's 3 oxygen atoms. If you look at the periodic table, 16 plus 16 plus 16 yields 48. 48 grams of O3 per mole of O3. Now these units will cancel now, moles of O3, so that what you have left in your answer are units in grams. And that turns out to be 7.20 grams of O3. Let's talk about a new type of calculation called percent composition. You'll recall from the lecture, the audio lecture, that percent composition is the amount of matter by mass in a particular molecule. So the percent carbon in this molecule here, this is the formula for TNT, is equal to 7 moles of carbon divided by the molar mass of this entire substance times 100. That will give me the percent composition of carbon. Let's do this example. Calculate the percent composition of each element in the formula of TNT. First of all, let's do the atoms, break them out. There's carbon, hydrogen, nitrogen, and oxygen. There's 7 carbon atoms. Each one is going to, each atom of carbon has a mass of 12.0 atomic mass units, or 12.0 grams per mole, which means I have how many grams of carbon in every mole of TNT. It's going to be 12 times 7. I'll leave this multiple sign here. 12 times 7, which equals 84.0 grams of carbon. There's 5 hydrogen atoms. If you look at the periodic table, each hydrogen atom is 1 gram per mole. So if you have 5 moles of hydrogen atoms in a mole of TNT, you're going to have, that's not 10.0 grams, it's 1.0 grams. That's my mistake. 1.0 grams per mole. I'm going to have 5.0 grams of hydrogen in every mole of TNT. there's 3 nitrogen atoms. Each nitrogen atom, if you look at periodic table, has a mass of 14.7 grams per mole. So 3 times 14 tells me I have 42 grams in every mole of 42 grams of nitrogen in every mole of TNT. Oxygen, I have 2 times 3 or 6 moles of oxygen per mole of TNT. 6 times 16 grams per mole gives me 96.0 grams of oxygen. So in 1 mole of TNT, I have 84 grams of carbon, 5 grams of hydrogen, 42 grams of nitrogen, and 96 grams of oxygen. If I sum each of the masses of the individual elements, 84 plus 5 plus 42 plus 96, I get 227.0 grams. This happens to be the mass, the molar mass of TNT. The total is 227 grams per mole. So my percent composition of carbon, therefore, is going to be 84 divided by 227. That's simply the mass of 1 mole of carbon divided by the molar mass of 1 mole of TNT, which is all of them. That times 100 tells me that I have 37.0% carbon. Do the same with hydrogen. 5 divided by 27 times 100, and I get 2.2% hydrogen. Nitrogen is 42 divided by 227 times 100, or 18.5% nitrogen. And lastly, oxygen is 96 divided by 227 times 100 equals 42.3% oxygen. So the answer to this problem tells me that in this molecule called TNT, I have 37% carbon, 2.2% hydrogen, 18.5% nitrogen, 42.3% oxygen. That's the percent composition calculation. Let's flip this pad and do another type of problem, just extending what we just learned about percent composition, and calculate an empirical formula. You'll recall empirical formula is the simplest whole number ratio of mole ratio of the atoms in any particular formula. Let's find the empirical formula if we're given the percent composition of glycine. Glycine, you may know, is the simplest of the amino acids that make up proteins. It has carbon, hydrogen, nitrogen, and oxygen in it. But the formula, let's pretend we don't know what it is right now. We just know it has those 4 elements. Let's calculate the empirical formula for this particular substance if we know the percent composition. So we're given this information. We are given that it's 32.0% carbon, 6.7% hydrogen, 18.7% nitrogen, and of course all the rest up to 142.6% oxygen. What we want to do is to find the numbers to replace these question marks here. What is my mole ratio? Now, if we're given this percent composition, let's assume, to make the math easy, that we have a 100-gram sample of glycine. If that's the case, if the total amount is 100 grams, that means we have what? 32.0 grams of carbon. If it's 32%, we have 6.7 grams of hydrogen, we have 18.7 grams of nitrogen and 42.6 grams of oxygen. So to replace these question marks with a number, we have to write in the number of moles of each of these elements here. Carbon, which I said in the 100 gram sample is 32 grams in glycine, is going to be 32.0 divided by, that's grams, divided by the number of grams per mole of carbon, which is what? Look at the periodic table, 12.0. Hydrogen is 6.7 in my sample size over here, grams, divided by its molar mass of 1.0. See, what I'm doing here is I'm getting the number of moles of each of these elements in this particular substance based on the composition. Nitrogen, if there's 18.7 grams in my sample divided by its molar mass, look in the periodic table, of 14 grams per mole. Oxygen, 42.6 grams divided by 16 grams per mole. So once again, I took my sample of 100 grams of glycine, which made my math easy. It meant if I had this compositional information in 100 grams, 32 grams will be carbon, 6.7 grams will be hydrogen, 18.7 nitrogen, 42.6 is oxygen. To get that to a mole fraction, which is what these numbers represent, I divide by the individual masses of these elements, which I got from the periodic table. 32 grams divided by 12, which is what the mass is of carbon. 6.7 grams hydrogen divided by 1. 18.7 grams nitrogen divided by 14. And 42.6 grams oxygen divided by 16. Again, these numbers on the denominator side are all obtained from the periodic table. That's going to give me a number of 2.66 for carbon. For hydrogen, of course, it's 6.7. Nitrogen is 1.33, and oxygen is 2.66. Now, these numbers all have fractions in it, and then by definition, the empirical formula is the lowest whole number integer of the mole ratio. So to get there, I need to now divide all these by the smallest number, which is 1.33. And when I do that, I get the empirical formula, which is the lowest whole number integer ratio of moles of elements to this particular molecule, which is glycine we talked about. So it's C2H5N1O2. O is also 2. That's the empirical formula for glycine. The last type of problem we're going to be solving in this chapter is called molecular formula. We'll get the molecular formula if we're given the empirical formula and the molar mass of a particular substance. Let's take as an example fructose. Well, you might know that fructose is the fruit sugar, like sucrose. It's similar in its formula. If we're given the molar mass of fructose, which is 180 grams per mole, and we're given the empirical formula, which is C1H2O1, perhaps this was determined in a similar way that we did the previous problem, if we had percent compositions of carbon, hydrogen, and oxygen. If this is our empirical formula, what is the molecular formula? Well, what we need to do is calculate what's called a multiplier, which is the formula of fructose, which is going to be a multiple, and we'll use N to represent that, divided by what the molar mass is of the empirical formula, C1H2O1. I'll go ahead and make it consistent, put ones. Even though there's no subscript, of course, you know that to be 1. What is that ratio? Well, we're given this number for the numerator. So we know the numerator is 180 grams per mole. What's the molar mass of C1H2O1? Well, one carbon has a mass of 12.0, hydrogen is 1, there's 2 of those, and oxygen 16. So 12 plus 2 plus 16 is 30, 30 grams per mole. 180 divided by 30, this gives me a number of 6. That's my multiplier used to multiply the empirical formula by. My empirical formula, C1H2O1 times 6 gives me C6H12O6. This is the molecular formula of fructose.